Thanks for the introduction. So today I'm going to talk about the ALTEQ, a digital signature from alternating Chinese-uniform equivalence. So this is the joint work with Max Blister, Dang, Anna Kumar Narayana, Thomas Planta, Yumin Chao, and Arlo Spasius. Okay, so let me first give an overview of the alternating Chinese-uniform. So we wrote GLN FQ to be the general linear group, which consists of n by n invertible matrix over the finite field FQ. So, and we have a form, phi is said to be a function or a map from FQ to N cross FQ to N cross FQ to N to FQ. The trilinear means if it is linear in all the three arguments. And for the alternating, we say like a trilinear form phi is alternating if there are two arguments, whenever two arguments of this form are equal, and then the form evaluate to 0. So we say that trilinear form is alternating. With these notions, we can define a group action of general linear group A belongs to GLNFQ act on trilinear form, which is essentially we use A transpose due matrix vector multiplication on these three arguments. Okay, so then we can define the alternating trilinear form equivalence problem. So that is easy. So given two alternating trilinear form, phi and psi, the question asks to find such a general linear group, find the invertible matrix belongs to general linear group A, sends psi to phi. So recently, Grocho and Chao defined a new complexity class, TI complete. Here, TI means tensor isomorphism problem. In this class consists of many problems that are polynomial time equivalent to tensor isomorphism problem. Also, the alternating trilinear form equivalence problem has been proved to be TI complete. And moreover, we have matrix code equivalence problem is also TI complete. And the linear code monomial equivalence problem can be reduced to alternating trilinear form equivalence problem. So it's more interesting. Based on these two problems, there are two signature schemes are currently submitted to NIST, that is MES and NEST. So it is very interesting. So the above three problems are of particular relevance and close. Okay, so now the question is based on ATFE, how do we design a digital signature? The construction is very clear. We have two steps here. First, we use Goldratt-Micali-Whitson framework, zero knowledge protocol, and based on ATFE, we design an identification scheme, and then we use Fiat-Shamir transformation, hence our identification scheme to a digital signature. So yeah, here is the GMW zero knowledge protocol for ATFE. First, we have public keys, phi0 and phi1, two alternating trilinear forms. And we also have a invertible matrix A as our secret key, which A sends phi0 to phi1. And at first, Anis or prover just generates a random equivalence B. B is also belongs to general linear group, which sends phi0 to psi as our commitment. And Bob will challenge a binary from 0 or 1 and sends back to Anis. For the response, Anis just sends either random instance B or the matrix here contains our secret key. is A inverse B. And for the check part, Bob just check either the response sends phi0 or phi1 to Psi. So yeah, it is well known for the GMW zero knowledge protocol satisfy completeness and soundness and Oliver zero knowledge. Before we apply Shamir transformation, we should, of course, reduce soundness error by lambda per 9 petitions. And here we also use two optimizations. The first one is we extend the challenge space, or called larger challenge space. With this method, our new public key includes say alternating trilinear forms instead of 2, and hence reduce the soundness error to 1 over C instead of 1 over 2. And the next one is unbalanced challenge space or fixed challenge space. With this method, we just need to respond to C instead of invertible matrix for the fixed positions on the challenge. And then we can just apply Shamir transformation. Turns out the identification scheme to a digital signature. So yeah, here I will review some algorithms and the complexity of the alternating transform equivalence problem. The first one is the direct global basis attack, and there are 3 modelings. The first one is direct cubic modeling. Here we have A as our variable matrix of n by n, of size n by n, and we just put A on one side, A transpose, that is A transpose act on the 3 arguments of A1, and that's our equations. The next one is the quadratic with inverse modeling. We will create a new matrix B as the inverse of A, and in this modeling we will add some a few more equations like AB equal BA equal identity, and then we will set more equations like this we do. We put A transpose at the first 2 arguments of phi1, but we put B transpose at the 3rd argument of phi2. And then we can also put A transpose at the first argument of phi1 and put B transpose at the last 2 arguments of phi2. And the third one is the quadratic dual modeling, currently proposed by Ran and Samagiska Tremoska. So they, first we can use a tuple of matrices to represent the alternating trilinear form. Like phi1 and phi2, we use x1 to xn and y1 to yn. And then we have L is equal to n choose 2 minus n. We use B1 to BL L matrices to span the orthogonal complement of Yi with respect to traces 0. So, and then we can settle equations for I belongs to N, J belongs to L. We set trace of A transpose Xi, A Bj transpose is 0. And also there is a trick. So we need to remove some invalid solutions because we just have one variable matrix here. So the result will contain some rank 1 matrix. So they add some cubic equations to remove the invalid solutions. Okay, so yeah, this modeling is very interesting, but based on an assumption here, is so-called, we have assumption for the system. We assume this system is semi-regular. So this assumption, which we are still working on understanding. The next algorithm is a family of graph theoretic algorithms. So we can define a graph associate a alternating trilinear form. So let A belongs to FQ to N be a vertex of this graph. If we have two vertices, we say A, B be edge. If and only if we instantiate A, B as its first two argument of phi, like phi A, B, W evaluate to 0, we say A, B be edge in this graph. So there are three algorithms I just briefly described here. The first one is of complexity big O of Q to the 2 over 3n, proposed by Bullinger, Fook, and Weber. So the basic idea is sample low rank points by brute force, and then find collision by apply global basis many times. The next one is of complexity big O of Q to the K. And here, if n is odd, we have k is equal to n minus 7. Otherwise, k is equal to n minus 4. And currently proposed by Bullinger. So the idea is sample low rank point instead of by brute force is sample by graph walking, and then apply global basis many times to find collision. So the last one is for big O of Q to the K over 2. The idea is sample low rank point by graph walking or solving min rank problem. And then we just need to do birthday paradox instead of apply global basis many times. Okay, so with this algorithm, we have the parameter choices. So here, lambda is our security parameter, R is the round, C denotes the number of alternating trilinear form in each round of public key. So, and K is the parameter from fixed challenge space. And we choose N by the first algorithm is direct global basis attack. And we choose Q by the graph theoretic algorithm. And here I put the public key, private key, and signature size in terms of byte here. And of course, we have the performance here. We have two modes, one balance and second is short signature. So as you can see, we use the same N and Q, but different RKC. So of course, we have public key size of 8 kilobytes and signature size of 15.9 kilobytes. Yeah, but in the short sig, we have increased public key size to be 52.4 kilobytes, and we reduce our signature size to be 9.5 kilobytes for category 1. Okay, so there is the timing for our scheme. We test our code on laptop of 2.2 gigahertz and with 12 cores. We have the balance mode for category 1. We have kgen. Timing is 0.39 megacircles. Of course, for the short sig, the kgen timing increased to 26.3 megacircles. But we in the short sig, we have decreased the sign and the verify time. Of course, there is ample room for the further improvement or enhancement in our implementation. So we will update soon, this or next week. For the verification time, we have about twice speed up for the balance mode and fourfold speed up for the short sig mode of the category 1. And we also plan to implement the 64-bit arithmetic or the AVX 512 in the future.